So what happens if you have a magnetic field? Let's say there's a magnetic field this way, B field, and you have a piece of wire that has current in it. Let's say it has current I in it. And because of this current is made up of moving charges inside the wire. Each charge feels a force in a magnetic field, and therefore the wire itself has a magnetic force acting on it. We want to calculate what is the magnetic force acting on a wire carrying a current in a magnetic field. So on each particle there is this much force acting, but V is the drift velocity of the charges, right? We can consider positive charges moving in the direction of the current, although it is negative charges moving in the other direction. The effect will be exactly the same. Let's say there's a charge Q that's moving along this wire at time delta t and distance delta f. Because delta Q over delta t is the current, delta Q is I delta t. But then the force acting on this part is Q or delta Q times V cross B. And then V is delta L over delta T, right? So if you put F equal to I delta T and times V cross B, and V delta T is delta L, right? Or V is delta L over delta T, with delta T cancels, this becomes delta L. So F is equal to I, we get delta L cross B. Right? But then if you add all the contributions, the I is constant, B is constant, you can just replace delta L by L. So the force on a wire, F, on a current carrying wire is I, you can call L cross B. And L is the vector that is the same length as the length of the wire, but it's in the direction of the current in the wire. Or if the wire is not straight or magnetic field is not uniform, you can say for a small piece of the wire, dF is equal to I dL cross B, because when you take it small enough, then field will be uniform around that, and you can use the same equation, and then you add all the contributions. The total F will be integral dF as vectors. So it will be I integral dL cross B. If the B field is not uniform or the wire is not straight, you can use this. But for a straight wire and uniform field, you can use this one. Okay? So this is force on a current carrying wire. Anyway, another thing that you can consider is that what happens if you have a loop of current in a magnetic field. Suppose this board, there's a wire around this, and this is in a magnetic field. Let's say there's a magnetic field like that, and there's a wire around this that carries a current in, let's say, in this direction. And if we put that in a magnetic field, what happens? How many forces are acting on it? I'm going to do this. So there's a magnetic field, let's say, in this direction. And I'm going to just draw a cross-section of this, okay? But this is a board. This is a loop of current. The cross-section looks like that. So it's like this. But there's one side, the current is coming this way, the other side is going the other way, and this side is going into the page, let's say. The current is going into the page, this side the current is going out of the page. And the other two sides, the near side is going this way, the far side, the current is going up, right? Is it clear what I'm doing? We want to see what are the forces acting on this and what is the net result of all of these forces. Let's figure out the force on each side of this wire. There's 4 wires, 4 straight wires. What is the force on the near side? That's the current is this way. Remember, B is this way, so you have to put L cross B. L is in the direction of the current. So if it is like that, the current is this way, and you have to turn it toward the B field along the smaller angle. See here, the current, draw that again. On the near side of this loop, the L is like that, and B is like this. When we say you turn the first vector into the second vector, you should be clear about you can go this way or you can go this way, right? But we always go from the smaller angle. So if you do that, you go from L cross B is a force outward, right? So the force of this side is outward. What is the force of the other side? It will be like L this way and B this way. I mean, L this way and if you B this way. Right? L cross B will be inward. So on the near side, the force will be outward. On the far side, it will be toward the page. So these two cancel each other, right? So we can just forget about those two. And then what about this one? What is the force acting on this side, which is like that? So that's L crossed by B, like that, right? B is this way, so it will be up, right? So there's a force this way. Let's call it F1. What about this one? Is L cross B, right? So there will be force this way. Let's call it F2. These two also the same magnitude and opposite direction, right? And then they cancel each other. But do they create a torque? Because they don't pass through the same line, they create a torque, right? So they try to turn this board in this direction, right? So they create a torque. I want to calculate the torque created by these. So if you take the middle of this board and draw a line here, what is the torque created by this force around this point, at the axis perpendicular to the board? Is it here? The torque of this force around this axis. Do you remember how to calculate torque? Who remembers that?
Force times distance.
Force times distance. Which distance? No.
Half of
Half
like
of
two. Yeah.
No, that force times distance. If the distance.
Yeah, distance like to the point in the middle.
You mean this distance?
Yeah.
No, if you want to use this distance, you have to also use the angle between them, right? Sine of the angle. You can say torque, remember torque is F times the R times sine of the angle between R and F. This is R, this is where the force is applying, R. And this is F, so there's angle between them, phi, here. You have to multiply by sine phi, right? So you can say the force F1, tau 1 is F1 times R, which is, let's say the length of this side is, this is, if this side is B and this side is A, right? So the board has the dimensions A and B, right? So it will be F1 times half of B, right? This distance from here to here, times sine of phi, which is this angle, right? And what about the torque of the second one? It will be this force, which is the same magnitude, this distance, which is the same, b over 2, sine of phi over 2. What is the direction of that? Are the directions opposite? Direction of the torques. What is the direction of the torque of this one? Torque as a vector is r cross f, right? Then the r cross f is perpendicular to both of them and it's out of the page. What about r cross f for this one? R cross f, out again. So they add up, they don't cancel each other. They are both in the same direction. So one of them is this, the other one has the same magnitude, the same direction, and also the same direction. So tau total is equal to twice tau 1. So tau total is equal to F1, B times sine phi. And what is F1? According to this. What is the length of that side? This side was B, the other side was A. So the length is A, the current is I, so it will be IA times the B field. And they are, what is the angle between that side and the magnetic field? If they have this side and magnetic field, the angle between that side and the field is 90 degrees. So the force magnitude will be IL times B only. So F is ILB, so net torque is equal to IA B sine phi. All right, so now this is I times the current times B field. What is A times B? The area. Sine of phi. I want to write this another way. I mean, write it for now. Total. I B the area sine phi. I want to define the area vector again. I want to write this in terms of area vector. The area vector is defined, we said that it's the same as the area, the magnitude of the area, but the direction perpendicular to the area, right? The direction can be this way, can be that way. Now that we have current, we can uniquely define that area. We say that the area vector is defined by a right-hand rule. If you put your 4 fingers in the direction of the current in the loop, your thumb shows the direction of the area. So it could be up this way or down this way, right? But now with the current, we uniquely define this area vector. It has magnitude of AB, which is capital A, and it is in that direction. All right. So what is this angle of this to the magnetic field? This is B field at this point, and this is the area vector. And you see that this side is perpendicular to this side, and this side is perpendicular to that side. So these two angles are the same. So this is phi. You can write the torque as I, the area of magnitude times B magnitude times sine of the angle between them. And you can write as I times area vector cross B, because this area, if you do A cross B, it will be in the same direction as the torque. But I want to also define something else. I times this area vector, we call it another vector mu. We introduce a mu vector, which is the current times the area vector. The area vector like that multiplied by the current that's going around the loop. This is called magnetic dipole moment of the loop. So you multiply the current by the area vector for that loop. How much current is going through the loop times the area, and it's a vector in that direction that we just defined. The torque will be IAB sine phi, and then we define mu like that. We call it magnetic dipole moment, mu. And then you see that this is the magnitude of mu times magnitude of magnetic field times sine of the angle between them. So tau can be written as a vector. The torque on a loop of current in a magnetic field is mu cross B. So you need to know what this means. This is a torque acting on the loop of current in a magnetic field. Mu is the magnetic dipole moment, I times A. Area vector has magnitude of the area, the direction that comes from right-hand rule. If you put your forefingers of the right hand in the direction of the current in the loop, the area vector is perpendicular to the loop and in the direction of your thumb. And torque can be written as mu cross B. You see that if mu, which is in the same direction, let me draw a vector mu here. This is mu vector. If this turns so that mu and B are in the same direction, this comes this way, the torque will be zero, right? The two forces will be in the opposite direction. So mu cross B will be zero if they are in the same direction. The torque will be zero. The torque becomes maximum if mu and B are in the perpendicular direction to each other. And of course, again, it becomes zero if they're in the opposite direction. So you see that if you have a loop of current in the magnetic field, it tries to align itself with the magnetic field. So that's why, for example, if you have a compass needle, it has like a loop of current. It has magnetic moment mu. It tries to align itself with the magnetic field, and that shows the magnetic field direction. Now, of course, if you turn this, it takes energy to turn it. The energy of the magnetic dipole moment in a magnetic field, the potential energy is equal to negative mu dot P. So if there's a magnetic dipole moment in a magnetic field and it's not aligned, it has some energy. It can do some work to get aligned to what they do in MRI. There's a magnetic field, they turn the spin of protons, and then when these are aligning back, they give you photons, and then they record that photon. They show where the photon is coming from. Of course, it's a lot more complicated than that, but this is the basic principle. They use this kind of energy to do imaging. So these are the basics of MRI, basically.